3D analysis and surface modeling. The moment you say 3D analysis, the first thing which will come across your mind is your surface modeling. We mention or we say that everything is a surface and we just try to model that. So, what are the various inputs or requirements for that? Where do you get the data, that is the source of your 3D, and how do you display the data and how do you analyze the data? Then once you display the data, you can visualize the data without much of analysis. In the sense, you can just try to rotate, go through, fly through, all this kind of visualization is possible. Well, you can also model the surface. Now, here it refers to the third dimension aspect and the surface which is already available in 2 dimension. Surface modeling is the most important thing which we do using 3-dimensional data. Visibility analysis, a kind of an analysis where we just try to understand any given terrain you want to go through or fly through, or you just have to visualize the data. When you have hidden objects, that is objects which are not visible from the point of view of your origin, what we tend to do in surveying, we just try to incorporate points in between, go to the new point, then from there you try to visualize the data. Something similar to that, visibility analysis is done using points which are known and points which are unknown, that is a little away from the unknown, from the point of your origin, go to another point, from there you try to look at the objects. Visibility analysis, how well you can visualize the entire area from your point of your origin. As I was telling you, the source, most important thing is that what we tend to do is that we use, say, converting your 2D data into 3D data. So, that is one of the major sources here. So, you use the 2-dimensional data, convert into 3-dimensional data, and you just look at it, you can see that what is supposed to be a 2-dimensional, if it is converted to 3D, will appear like that. Otherwise, it will be a plain surface, you will not be in a position to see anything. Here you will be able to see the objects which are protruding above the surface, and you can also see some of the objects like your, say, drainages which is passing through the hilly terrain. So, that is a simple example of how to convert it and how to use it. How do you convert the data? Basically, what we try to do is that we have a simple data, you can see here a 2-dimensional data which could be a point data, it could be a country or a continent, wherein which for every given point you may have a data. Based on that particular point, it may be a population data, it may be a kind of elevation data, it may be water depth data, whatever it is, you can create a third dimension here. So, based on that, what we tend to do is that we use this 2-dimensional data based on the z value for every point which is acquired, we create a third dimension. See, converting your 2D data to 3D data, a simple method of doing it. Of course, there are also other methods. Here I was just telling you something about, say, your population data. So, you know that in a given terrain, various these are districts of a particular state in, say, southern part of India, that is your Tamil Nadu, wherein which you find various districts here. These districts are shown as it is in 2 dimension and each of them are named. So, do not worry about that particular part. Now, coming to the aspect of how to visualize that, very simple, isn't it? So, for every district you may have something like, say, the total population given in the district. So, once I know the total population, I want to visualize that. So, by looking at the map, I will not be in a position to see what exactly is present, how they are different, how different each of the districts are. So, when I am using a third dimension, it becomes much easy for me to understand which of the districts are having higher population, which are having lower population. A simple way of representing the data, you model this particular surface using the z value. Here the z value is your population data. Similarly, as I was just telling you, we can also see how to create that in a 3D scene, a document which is normally available in ArcGIS, because they are a popular software, I have just chosen that. You use that and then create a 3D scene, and this will be your input and this will be your output, a new document type will be generated. What are the data sources for 3D display and kind of analysis? Grid data sources, the data which is available in the form of a grid. Invariably, all kinds of analysis, when you are just trying to work, whether you go for a vector data or raster data, this raster data or vector data can be converted to a grid for raster analysis of the data. Here this particular conversion of your raster data into a data which is compatible for analysis is your grid data. So, this will become one of the more important inputs into your say your 3D analysis. Tin data sources, but many times you do not expect or get anything like a third dimensional data in your raster. So, in that context what is that you are supposed to do? You use your tin data, triangular, this is your tin part of it. So, this data source which will form a very important input into your say 3D data analysis is nothing but your vector data. So, you use this either raster data grid source or your vector data tin source. You can convert 2D shape files which are already available with you in different forms and the raster data. So, this is another set of data which is available for you. 3D shape files, many times data may also be available in 3D shape files itself rather than a grid data or a 2D shape file. So, this could be one of the inputs. Grid data sources, the first one what we are just looking at. So, where from you get normally from say spatial analyst. So, it is very convenient and easy for you to convert. So, the method of conversion is not being taught to you, how to approach a particular problem, how to generate your input data, how to analyze will be the crux of your topic today. Well, so what we use that? Use your spatial analyst, one of the extensions of your ArcGIS software, convert the data, use that particular data and then convert the data into grid data and utilize that. That could be one of the resources. Or any other data which is supported, did not necessarily be in a specific software or a specific extension, it could be any other software, any other data source. You have vertical mapper in your map info, things like that. So, that sort of a thing can be used. And the next important thing is your DEM. So, this we have seen in detail earlier, just we will be using the output from the analysis from that particular method of creating a DEM as an input into your 3D analysis. Downloading a DEM data. DEM data is available over net, which is being supplied by various agencies. One is your SRTM. So, this is a very interesting one and it will be of good quality also. Of course, there are so many other days. You can also create your own DEM. It is not that you have to depend only on the DEM which is provided free of cost or which is available on the net. So, we use the DEM which is available over net, or we can create our own DEM as one of the input sources for your grid. Then there are certain data which will have a I was just telling you data 3D data which is based on your cell values. So, the Z value can be the cell value itself. So, as you know that we use your grid network, namely your X and Y, which will be displayed in rows and columns. For every row and column, we will have a cell or a pixel, we call it as in terms of your remote sensing. In general, it is called as a simple a matrix of your X and Y. So, rows and columns, and each of the cell will have a value, and the cell value itself will be the Z value. So, that also can be utilized here say as one of the inputs for your grid data. DEM, I was just telling you how DEM can be used and how well DEM becomes a integral part of your 3D analysis. So, which is telling you DEM, digital elevation model, or DEM it is otherwise called as. It is nothing but a grid of squares and also many times known as a height map when it is actually representing an elevation, or it could be a vector based map. I was telling you of the tin part of it, triangular irregular network of the tin. This is one of the important inputs along with your DEM, a raster and a vector data. In a tin DEM data set, this is also referred to as a primary data, which is a measured data, which is measured from the field and then generated and created. Whereas a raster DEM is referred to as secondary data, it is nothing but a computer data. I am just telling you the tin mostly vector based, DEM raster based. The tin DEM is a primary data or a measured data, whereas raster DEM or your data which is raster format is referred to as a secondary or the computer data. I was just telling you other thing, the other methods of acquiring DEM data. as a very I do not call it as a very costly process, but it definitely relatively expensive process. You can use your LIDAR or IFSAR, interferometric synthetic aperture radar, or by a normal ordinary land surveying methods. So, these are some of the methods through which DEM can also be acquired. So, photogrammetric techniques, one of the very effective and sensible method of generating DEM data, but again a very expensive data. LIDAR is also another method. Of course, now it has become a very common thing using LIDAR data over field for urban applications. A lot of people are working on our LIDAR data, though it is an expensive process, but still it is a very one. So, this is one of the costliest, this will be relatively costly. Of course, these are all not provided by, cannot be generated by individuals, it has to be provided by some organization. Well, land surveying, it can be done by ourselves, that is we ourselves can use a total station, go to the field, get the Z value through various methods in land surveying, and then that can be integrated in a GIS environment after converting a non-earth coordinate to your earth coordinate system. So, this is one of the methods of acquiring your say DEM data. Where do you use the DEM data? So, very important. So, when you are using or it could be built using the data something like say using remote sensing technique. So, you need not depend only on your say land surveying. Again, though it is, I was telling you, it is relatively easy, you can use when compared to other 2 or 3 methods. This is again a costly affair and it requires a lot of manpower, but of course, you have another method, remote sensing techniques. I was telling you photogrammetry is one of them using aerial photographs, remote sensing another one where in which you use your satellite data. The major advantage you find in satellite remote sensing is that over a period of time, they found that they can use or create 3D models or acquire data of a same point from 2 different viewpoints. That is how we normally perceive. 3 dimension is perceived by human beings because with 2 different position or location of your eyes, we are able to see a single object and you are able to perceive the depth. The same concept is used in your satellites also. The satellites are designed in such a way that you will be in a position to tilt the satellite in the sense the sensor. See, the satellite will be passing through one particular point to another point. So, it will take a part of the land and then just goes to the next point. By the time it goes to the next point after a particular distance, they just tilt the sensors in such a way they will be looking at the point which it has passed already, a technology which was not hitherto for a long time. And now it is available. You are able to do the same thing and then we are able to tilt the same sensor looking at the same point from a different angle because you already moved from the first point of view. So, you go to the other point and then get the data. Obviously, as you are looking at the same point from 2 different angles, you will get the depth part of it. So, remote sensing, especially satellite remote sensing, has become a very common input for generation of all your DEM. I was telling you about DEM, the other one is called as your digital surface model or otherwise called as your DSM. So, it just captures the natural and built-in features of your earth surface. So, whatever you have on the earth surface that can be created as a DSM, digital surface model. This is very much useful in say especially in your telecommunications, urban planning, aviation and forestry. So, this what it does is it just extrudes the object from the surface. So, when it extruding the object, it will become much easier for you to analyze the data rather than looking at the same object in a flat terrain. So, a DSM will be something like an object over another object. So, you just try to understand what is present on the surface with using your 2-dimensional terrain. So, you model that. We have another context called as your digital terrain model. So, what it does this particular DTM, DSM is for your say natural and your built-in objects, where in which when you are trying to use features, natural features like ridges, break lines, which are all normally regularly spaced points. So, from a data set comprising your regularly spaced points and the natural features which are ridges in the hills, a DTM is generated. So, this augments a DEM by including the say your linear features of the bare earth terrain. So, normally whatever you have on the earth surface, a digital elevation model will be there, a terrain model will be a kind of a superimposed. You can see this how it is superimposed. What are the uses of your DSM? Where do you use DSM? As I was telling you, it normally refers to most of your say built-in features and natural objects. So, for landscape modeling, which is one of the most important thing, most of architects take up. City modeling. Now, people are talking about various ways in which you can develop a smart city or an Amrut city, improving the existing city. It is not that easy to do that. So, what we tend to do is we use your technology by which you can create your own, because a very important input into your smart city is your satellite data. It is not possible for anybody to visualize from the surface or from a lab what is surrounding an existing city or a town. So, the major advantage here is that we use the satellite data. The satellite data forms as one of the major inputs into your planning, be it whatever method of doing it. So, what we try to do is to model or generate or create a new city. We use the satellite data depending upon your requirement, depending upon the application. That particular thing will decide what could be the possible resolution. However it is, whatever is the application, this sort of a city development requires a high resolution data. So, we use a high resolution data as one of the inputs into your this particular study, and then we have the advantage of covering the existing town and also the area to be expanded. These two put together, we can cover the entire thing using 1 or 2 or 3 scenes, depends on your satellite and the path and the row, which we have seen earlier in remote sensing. You acquire that data, stitch them together, and then try to demarcate the existing boundary and the supposed or the suggested boundary. A very important application is your, as far as your city modeling is concerned, where your remote 3D and 3D visualization as well as your basic data will be true to 2D. You can just demarcate the data initially, then start working or visualizing on your 3-dimensional data. City modeling is one particular aspect. As I was just telling you just now about the visualization, how do you visualize that? To visualize that data in 3 dimension, you need some inputs that we will say a little later. So, a 2-dimensional model can be created into a 3-dimensional model based on the existing objects which is present on the earth surface, and then you can look or visualize what could be the possible or the tentative method of representing, what could be the way in which objects can be represented in the future, a kind of a visualization done by your architects. DTM or the digital terrain model, which is required basically for some of the simple applications. For example, flood or drainage modeling. So, when you are working on a specific thing, like I was telling you the city, you can go for a DSM, because every objects there, every building can be considered. When you are talking about a larger area where in which a kind of a flood is taking place, or you are interested in modeling the drainage characteristics of that particular basin. Flooding, even in cities, it is very much pertinent. As you are aware, in the city of Chennai, we had a huge floods in the month of December last year, and they are predicting much larger rains and much more flooding this year. And I can't say it's unfortunate, but the most difficult thing to be digested this year is that the water levels are already up. Last year, the water levels were so low, we were able to tolerate for 1 or 2, 3 rains, only the 4th one smashed the entire city. But this particular year, the water levels are relatively high in most parts of the city. So, if the drainage system is not proper, if the floods are not controlled or it is not let properly into the sea or any other exit point, it is going to be a huge difficult thing for the authorities to monitor that. So, such a modeling, you see, such an important thing I am telling you, where need not necessarily be in a civil engineer, an architect also can plan such studies. So, namely DTM is relatively or mostly applied inside something like your flood or drainage modeling. Of course, land use studies, as I was telling you about the smart city modeling, the existing land use your DTM. you superimpose your land use map on your DEM, that is, you are already an elevated object. DEM is nothing but elevation model, and then that will become your DTM, digital terrain modeling. The entire terrain model, of course, you cannot be in a position to edit instantaneously, but with the advent of your various application in your software, now you also have the advantage of editing the data in 3D using your GIS Pro, that is ArcGIS Pro, a relatively new software which not been practiced by many people, and a huge scope for the students who are already doing architecture. Along with the knowledge with the architecture, you can also use this particular software, namely ArcGIS Pro, and then we will be in a position to do much better way of representing objects with respect to your application. Land use studies is that. Of course, other common applications here, geological applications may not be directly pertinent to you. Geological applications, the creation of a volcanic eruption, the formation of earthquake. How do you visualize an earthquake, occurrence of an earthquake? Okay, the more popular term known to you, us in fact, is a tsunami. So, creation or generation of your kind of a model where in which you can predict a tsunami. But tsunami, as it is not predictable in sense, you cannot tell when exactly it will take place. What could happen? What will happen to the terrain if a tsunami is triggered? So, that is sort of a study. So, geological applications very commonly they use in this applications. Of course, there are other applications where in which I was just telling you about, not only just your tsunami or flood or earthquake, any kind of other application, volcanic application, all these things can also be used. They can use your DTM and then generate it. In fact, we can also talk about, say, something like forest, a kind of representing a forest or visualizing the forest in the laboratory. Many a times, in fact, the very essence of remote sensing, its popularity grew only because of accessing inaccessible areas. Indirect accessing, I am not trying to say, is directly accessing the data. Accessing inaccessible areas has become the key word for the success of remote sensing, especially in forests which are evergreen in nature. It is not possible for one to enter, and even if you enter, it will be difficult. We do not know how it to come out of it, unless otherwise you have a very high end equipment like a GPS, which will show you the way in and way out, and that too provided you are not able to have the equipment exposed to something, to the say open sky. Well, so coming back to this sort of, so this sort of an applications can all be done using your DTM. Whereas when you come to your architecture purpose, especially your landscaping modeling or city modeling or visualization, you use your DSM. TIN data sources, I was telling you, triangulated irregular network. One of the major things is that what we try to do is we create or generate what is called as your irregular triangles. There will not be any regular triangles in TIN. As you see here, you have the triangle 1 and triangle 2, just joining points of various elevation. When you join the points are not equally spaced, that you have to bear in mind. Various given a well organized buildings, probably you may have a similar height, but if the same well organized buildings, if it is in a terrain where it is undulating in nature, you do not get the same height, isn't it? So, one building will be here, the shape of the building, the size of the building, height of the building, everything will be same, but its elevation with respect to MSL will change. So, it is not possible to get the Z value uniform throughout and also the position of that. So, only in terms of a well organized building structures, then you can get a position at least, but otherwise it is not possible, Z may be varying. Well, coming back to the TIN part of it, it joins all points of different elevation into triangles. Just join 3 points, obviously you will get a triangle. Then that is actually generated, and then you use the different types of vector data for doing that. As I was telling you, triangulated irregular network, creation of a irregular network of triangles. You can use either the point data, line data or the polygon features, anything could be an input into your TIN data source. Where you want to create complex structures and so that you will be in a position to model a surface, that will one of them you can see here, where in which you find the entire area. You also have the contours and also the drainages which are running across. So, this sort of a thing where in which you have two different aspects, namely the contour and the say your drainage system. You want to visualize the flow of water, for example, then this sort of a model will be very important, because here you know the z value through the contour part of it. Create that tin, because you can just convert these lines into point data, or you can use the lines itself as input into that. Create the tin, and then once you create the tin, as I was telling you, incorporate or superimpose your drainage map over that and analyze. So, that sort of a case you require that. You can see here the same contour data, how it is converted into your tin. You can see the complexity of the data. The closer the contours, you know that the steeper the area. So, you can see here in those places where the contours are relatively close, you find they are steeper, whereas these are the empty or the blank spaces where this will be the last line, and then followed by a longer distance. After longer distance, you will have another line. So, these are all relatively flat terrain when compared to the surroundings. Well, coming back to this, we find that this particular entire area, entire zone or the part, you find that it is divided into n number of triangles. The total area is divided into triangles, and then that is actually used as one of the inputs into your say tin for tin generation. So, you can see here when I just try to zoom that area. So, from your contour data, simple contour data, and your drainage which is already available from various sources, namely a topographic map or any other method of mapping, you create the tin surface from this input and then generate a 3D model. Now, on viewing this, you will be in a position to see that how complex it becomes. How does this water bodies, all these your drainages, how does it flow, from which direction to other direction. So, this will be the demarcation or the points of highest elevation in a given terrain. For watershed analysis, any kind of a study for that, it need not necessarily be for your say topographical survey or analysis or your say civil engineering application. For all kind of studies, what one does is takes into consideration your watershed boundary. This is the boundary. We say that all water which is falling on this side will go and travel to these drainages. All the water which is falling the other side of this particular ridge or the peak point will go to the other side. So, this sort of understanding of the terrain, which is a very complex one, you cannot just like that visualize that, isn't it? So, it is not possible to look at it at a two-dimensional data and say, oh, what could be the possible movement of water. Well, so a three-dimensional generation of this particular tin using your input data from the field will create a 3D model, and you will be in a position to understand or visualize various things depending upon the application part of it. Thank you.